So now that we understand what concavity is, the shape of a graph, again being concave up means it looks like a smiley face or a cup, concave down means it looks like a frown. We want to find the intervals of when it is concave up and concave down. Again, the way that you find when it's concave up is you look for when the second derivative is positive, and the way you look for when a function is concave down, you look where the second derivative is negative. So this first problem here asks us to discuss the concavity of the graph. We need to start looking at the second derivative. So if we look at the first one, a, f of x equals negative 2x squared, the derivative of negative 2x squared would be negative 4x. Again, that's the derivative. We don't care about the derivative. That tells us increasing and decreasing. What we actually want is the second derivative. The second derivative of negative 4x is negative 4. Notice there is no x here, so it doesn't matter which value of x that we're talking about. This is always going to be negative. So if we look at the domain of the original function is a quadratic function, which is a polynomial function. The domain of this function is negative infinity to infinity. When the domain of a function is negative infinity to infinity, we need to consider the entire real number line. Notice the second derivative is always negative. It's never equal to 0. So that means on the entire interval, the second derivative would be negative. Anytime the second derivative of a function is negative, we know that the original function is concave down. So, where's this function concave up? Never or none. Where's this function concave down? On its entire domain, which in this case is negative infinity to infinity. This is one of the rare test cases when you don't have a point where the second derivative is equal to 0 or undefined, that you don't need to break up the number line and you don't need to actually pick test points because the derivative was always negative. So now let's look at the second function that they give us here. The second function that they give us is negative 2 times the square root of x. Negative 2 times the square root of x does have a restricted domain. The domain of this function is 0, including 0, because we can plug in 0. So that's a bracket 0, comma, infinity. So from 0 to infinity. Again, if we want to know the concavity, we have to look at the second derivative of the function. So anytime you want to take the derivative of a radical, I changed it into exponential form. To find its derivative, I use the power rule. I bring the 1/2 down. So I have negative 2 times 1/2 x to the negative 1/2. The 2 simplify, I end up with negative x to the negative 1/2. Again, though, I don't need to simplify this because I don't care about the first derivative. The first derivative tells me increasing and decreasing. I care about concavity, so I want the second derivative. To find the second derivative, I use the power rule again. So I'm going to bring down the power, and then I'm going to subtract 1. Well, a negative 1/2 turns into a positive 1/2, and then I'd have x to the negative 3/2 when I subtract 1 from the power. This I am going to simplify and write in proper form because I do care about the second derivative. So because it has a negative exponent, I throw it into the denominator. Now I have 1 over 2 times the square root of x cubed. Again, what I notice is my original function was restricted. My second derivative has to be restricted as well. The only difference is I can't actually plug in 0 into the second derivative, because if I plugged in 0, 0 cubed would be 0, the square root of 0 is 0, and I'd end up with a division by 0. So this one, instead of the domain bringing a bracket 0 to infinity, it's actually a parentheses 0 to infinity. I cannot include the number 0. So what test point do I use when I'm looking at the number line? All I care about on the number line is numbers bigger than 0. And I can plug in any number I want. I can just plug in the number 1. If I plugged in 1 into the second derivative, I would notice that the second derivative of this function is positive. And any time that your second derivative is positive, you know that your original function is concave up. So where's this function concave up? This function's concave up on the interval 0 to infinity. Notice that is a parentheses. We cannot include the number 0. And it's concave down nowhere. So let's put all of this together in a single problem. What if I give you a function and I want to know when is this function concave up, when is this function concave down? Again, concavity, we're going to be looking at the second derivative. I apologize as this problem is going to have some bad numbers, but that doesn't stop us from being able to do it. You will want a calculator to help you simplify and get some numbers to help you get some test points on this one. All right, again, so the idea is we want to find intervals of concavity. To find intervals of concavity, the first thing we need to do is find the first derivative. I am going to note here that the numerator of this function is a constant. So what I'm going to do is I'm going to look at this original function as 6 times x squared plus 3 in parentheses raised to the negative first power. That way I don't have to use the quotient rule when finding the first derivative of this function. So let's go and find the first derivative now. The first derivative using the power rule would be 6 times, I'd have to drop the negative 1. I still have the x squared plus 3, keep the inside the same. The power would now be a negative 2 because I have to decrease 1 from the power. And then never forget to take the derivative of the inside. The derivative of x squared plus 3 is 2x. So let's clean all of that up and see what I end up with. It seems to me like I would have a negative 12x all over x squared plus 3 quantity squared. So that's just the first derivative of the function. To analyze concavity, I need to find the second derivative of the function. So let's look at the second derivative of this function. To find the second derivative of this function, I'm going to use the quotient rule. The quotient rule states that I should do the bottom, which is x squared plus 3 squared, times the derivative of the top. The derivative of negative 12x is negative 12, minus the top, which is negative 12x, times the derivative of the bottom. Again, I'm going to use the chain rule, which would be 2 times x squared plus 3 raised to the first power, times the derivative of the inside, which is 2x. All of that is over the bottom squared, which would be x squared plus 3 squared, quantity squared, and then square that entire thing. A squared squared is going to be a fourth power. So now what I want to do is I want to factor out anything these things have in common. It seems to me like both of these terms have an x squared plus 3 that we could pull out. They even have a negative 12 that we could pull out. So I'm going to factor those out of the numerator. I'm going to simplify the denominator. Let's see what we end up with. I factor out the negative 12, and I factor out an x squared plus 3. It seems to me like in my first term, I'm going to have an x squared plus 3. And in the second term, if I factor out a negative 12 and an x squared plus 3, it seems to me that there would be an x, a 2, and a 2x left. Multiplying those together, so a 2x and a 2x would be a 4x squared. We do have the negative sign, so I'd have minus 4x squared. In the denominator, I have the x squared plus 3 raised to the fourth power. Why do I like to factor it? Because a lot of times you can simplify. For instance, I see here in the numerator I have an x squared plus 3. Here in the denominator I have an x squared plus 3, so this would turn into x squared plus 3 raised to the third power. And then I'm going to combine like terms in the parentheses here to simplify for my final step. Let's see what we have. I'm ending up with f double prime of x equals negative 12 times, looks like I would have a negative 3x squared plus 3, and on bottom I'd have x squared plus 3 raised to the third power. So the question is, I have two separate questions. When is the second derivative equal to 0? And when is the second derivative undefined? I need to find those points because those are where I'm going to break up the intervals. Well, a fraction is equal to 0 when its numerator is equal to 0. And a fraction's undefined when its denominator is equal to 0. So let's solve each of those equations individually. The first equation, I'd divide both sides by negative 12. Once I do that, I'd have negative 3x squared plus 3 equals 0. I'd subtract 3 from both sides. I'd have negative 3x squared equals negative 3. Divide both sides by negative 3. I'd have x squared equals positive 1. Take the square root of both sides. Remember, there's plus and minus when you take the square root of a square. And I'd be ending up with x equals plus and minus 1. Now, these aren't possible critical values because critical values are when the first derivative is negative, but these are very important points. I'm going to write right now, you don't need to understand it, but I'm going to write possible IPs, that stands for inflection points. What you need to realize right now is this is where we have to break our number line up. So let's continue and look at where's the second derivative undefined. Well, I'd take the cube root of both sides to get rid of that cube. If I take the cube root of 0, I get 0, so I'd have x squared plus 3 equals 0. I'd subtract both sides, 3 from both sides. I'd have x squared equals negative 3. And then I'd notice here I have a square equals a negative number. That can't happen. So where's this function undefined? The answer is nowhere. Okay. Or sorry, more so, when's the second derivative undefined? The answer is nowhere. So it seems to me like the only places I need to break this number line up is at -1 and 1. So let's go to the next step, which is creating our number line. I'm going to create a number line here. I'm going to break that number line up at 2 places, at -1 and at 1. Now I'm not looking at the first derivative, I'm actually looking at the second derivative of the function. I know at -1 and 1, my second derivative was equal to 0. It was never undefined. And the question is, what happens to our original function? Is it concave up? When is it concave down? I look at my first interval. My first interval would be -infinity to -1. My second interval would be -1 to 1. My last interval being 1 to infinity. I create a sign chart. I have my x values, and here's what's absolutely key about this. Now, instead of plugging it into my first derivative, I'm actually plugging it in to my second derivative. My second derivative was -12 times -3x squared plus 3, all over x squared plus 3 quantity cubed. I need a test point for each one of those intervals. I'll use the numbers, I don't know, how about -10 for the first interval, zeros between -1 and 1, and 10 for the last interval. Again, I don't care whether you're using a calculator at this point in time, if you're plugging it in by hand. Really just think about what happens to those numbers and determine whether each one of those is positive and negative for each interval. For instance, if I plug in a -10, the -12 would give me a negative number. -10 squared is 100 times -3 would be -300 plus 3 would be a negative, so that's a negative times a negative. All over the bottom, I know that any number squared plus 3 is positive, and a positive number cubed is positive. So no matter what goes in the bottom on these ones, I know my denominator is going to be positive. So when I plugged in -10, I got a negative times a negative, all over a positive, which has to be positive. Let's look at 0. 0, I'd have negative from the -12. 0 squared times -3, that's 0, plus 3, that's a positive number. A negative times a positive over a positive is a negative. When I plug in 10, I have the negative from the -12. 10 squared is 100 times -3 is -300. -300 plus 3 is a negative number. A negative times a negative over a positive, again, must be positive. So it seems to me my first interval, the second derivative must be positive. The second interval must be negative. The third interval must be positive. Again, anytime your second derivative is positive, your graph is concave up. Second derivative negative means it's concave down. Last interval, second derivative positive, means it's concave up. So we go down to the question, and we look at what are its intervals of concave up and concave down. Concave up would be -infinity to -1, and also 1 to infinity. Concave down would be -1 to 1. That's how you determine the intervals of concavity of this function.